Hi, today's lesson is 5-6, and it is on angle bisectors and perpendicular bisectors. As you listen to this, you need to participate in the examples. You need to stop the presentation so that you can finish taking notes. You need to do the constructions that I lead you through. Okay, the term equidistant should sound like it means equal distances because that's really what it means. It means the same distance from something. So we can have a point that is equidistant from other points, like this point P could be the same distance from X and Y, that length the same. Or we could have a point that is the same distance from a line going that direction, or this direction. So the term equidistant simply means the same distance from something. Like Seward might be equidistant from Lincoln and York. That point is the same distance each way. I'd have to really grab a map and see if that's true. Okay, a perpendicular bisector. We have dealt with the term bisect, like a midpoint cutting in half. We've also dealt with the term perpendicular, meaning that you're forming a 90-degree angle. Now this puts both of those together. So pause and write the notes. Then draw a diagram that goes with it. A perpendicular bisector is a segment, ray, or line that's perpendicular to a segment at the segment's midpoint. Maybe I should have written in there the explanation of perpendicular, but you should know that by now. Okay, so this line, L, is perpendicular and bisecting, meaning that this point is the midpoint of segment AB. If that were not the midpoint, it would just be perpendicular. If it was not forming a 90-degree angle but went through the midpoint, it would not be perpendicular. So you've got to have both parts together to make a perpendicular bisector. Okay, so I want you to create a perpendicular bisector so that we can do some exploring. Now to do that, I left some of that patty paper. I want you to grab a piece of that and make a segment AB on that patty paper. Go do that. Okay, now take your patty paper and fold it so that point A and B will match together, and make a crease down the middle. So that red line that you see should be your crease when you unfold your paper. Okay, now what I want you to do is make a point on that perpendicular bisector, and with your ruler, measure from P to A, and then measure from P to B. You can measure in either inches or in metric, it doesn't matter for me. Do the measuring and start this up again. Those two measurements should be the same. So maybe I got 2 inches and 2 inches. They were identical. Could try this again. Try a point even higher. Measure to each end. And in my picture that's going to be longer, but actually they're still going to be equal. So maybe this is 3 1/4 and 3 1/4. No matter where we put a point on that perpendicular bisector, when we measure both directions, those lengths will be equal. So in terms of that vocabulary, we would say, for instance, point P was equidistant from A and B, or point R is equidistant from A and B. Of course, this point M is going to be equidistant because wasn't M the midpoint if we made a perpendicular bisector? Okay, so here's the theorem that goes with what you should have just explored. So your notes again. Theorem 5.4, perpendicular bisector theorem. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. And I'm going to put back that picture that I had on the last screen. P, let's say that this is a perpendicular bisector. So then I'll change the color. PA is going to be the same distance as PB. Okay, pause the presentation until you're done with your notes. Okay, an example problem. Notice on this one that we have a line, and I put some markings on the diagram, perpendicular, and then the tick marks to indicate that it's bisected, so that would be the midpoint. Find the value of x. I do want you to notice by the tick marks, if that part is 12, then this segment is also 12 because that was the midpoint, it was bisected. Okay, to apply the theorem that we're working on, this point P is the same distance from A and B. Why? Because P is on that red perpendicular bisector. And the theorem said that it's equidistant from the ends of the segment. So to find x, 5x equals 20. Divide by 5, so x would be 4. Perpendicular bisector theorem. Another example, I turned the diagram this time, but look at the markings again. So this point P is on the perpendicular bisector. So if I label this point A and this B, again, A or P is equidistant from points A and B. So to figure out x, 5x plus 12 equals 8x. To solve, divide by 3. X is 4. Let's check that one and make sure that our two lengths came out equal. So to check it, I'm just putting a 4 in. So 20 plus 12 should be 32. And on the other side, 8 times 4, that's 32. So both segments did end up the same length. Okay, this is a related problem. It says, what type of triangle is MTS? Now, if you look at the angles, you might say it's an acute triangle. Okay, I don't disagree with that. Not what I intended, so let's keep going. Okay, if you apply the perpendicular bisector theorem, M is a point that is on the perpendicular bisector of MN. So MT and MS would be the same length because M is going to be equidistant from T and S. Now if you look at the markings on the great big triangle, you've got two sides that are the same length, and then the TS is different. So a triangle with only two sides congruent would be called isosceles. So it's isosceles. If you want to put acute, I was after the idea of at least the isosceles. We can use the perpendicular bisector theorem to do a story type problem. What if we wanted to find one place that's equidistant from Seward, Garland, and Milford? Let's say you're trying to build your house, and you work one place spouse works another place, or maybe the kids go to school, whatever story you want to make up. Let's make up, or let's try and find the point that is the same distance from all three towns. Okay, this is really just applying your perpendicular bisector theorem. So you would go from Milford to Garland and then do the perpendicular bisector. And we will do this construction in a little bit. So with those two, go from Milford and make an arc. Go from Garland, do the same arc, and then connect those. That is the perpendicular bisector of that segment. Now if we switch to Milford and Seward, let's do that same thing. From Seward, make an arc. From Milford, do the same arc. Connect those. Where those 2 points cross will be the point I'm looking for. That point will be the same distance to Garland, to Seward, and to Milford. And my sketch might not look perfect because, again, I was just sketching it. But as you use your construction tools, you should be able to come up with something that would be exact. So once we close it up and have all three perpendicular bisectors, there is an interesting property. Your textbook did not make this as a theorem, but it is something I want you to notice. Let's say this point P, and we'll label this ABC. Okay, that point P is on all those green perpendicular bisectors. So that's kind of the point that you found on my last example. So the distance, if P is on the perpendicular bisector of AB, then P to A is the same length as P to B. Turn your paper or turn your thoughts. P is on the perpendicular bisector of CB. CB. So P to C and P to B are the same length. Again, if you think about turning it, P is on the perpendicular bisector of CA. So then, as we've got marked, PC and PA are the same. So all of these red segments are the same length. P is equidistant from all the vertices of the triangle. So it says find some lengths on this one. So let me put some numbers up here. Let's go with this side is 30. This one's a little bit shorter. Let's go 24. And the bottom is 26. So if we have midpoints on the sides, that 30 would be split into 15 and 15, 12 and 12, 13 and 13. And if I tell you that from P to C is 20, P to A is also 20, P to B is also 20. So there are some lengths that are the same. And where did I get the 15, the 12, and the 13? I divided the whole side by 2. If the whole side is 30, then each smaller part is 15 because of the midpoint that's going on. So on these diagrams, be careful. I think on some of them they might give you one of the 13s and you come up with the other 13. So look to see what measurements are there. Okay, the next part is distance from a point to a line. It's the length of the perpendicular segment from the point to the line. So again, pause so that you can write down the notes. Then here are my sketches. From point P to this line, I would have to go perpendicular. That is the distance, or the length of that would be the distance from P to that line. Now, if you went at a different angle, you're gonna get longer segments depending what angle you're at. We don't want the length to be a lot of different possibilities, so we define that the distance is the exact perpendicular. So on the second one, it's at a slant. The perpendicular is probably about in there. I didn't do that very well. Let me try it again. Let's use a drawing tool. Oh, I lost my point. Okay, so a drawing tool would probably work better. Marking it so that it is at a 90-degree angle. Okay, now we're going to switch to angle bisectors. I need you to grab a protractor because I'm going to have you do that with the protractor. An angle bisector, I know we've talked about before, cuts an angle exactly in half. So I need you to grab your protractor and make yourself an angle similar to what you see. Measure that angle. Yours is going to be different than mine. When I measure mine, I get 80 degrees. Now if I want to create an angle bisector, 80 divided by 2 is 40. So lay your protractor down again and measure around how far is 40 degrees. And create the angle bisector. This can be done by paper folding, but it's hard to do. Hey, the bell's going to ring here. Don't be alarmed. Okay, now that we have an angle bisector, we're going to try and see if we can get this bisector idea straightened out or understood. What it's going to talk about is a point on the angle bisector is the same distance from each side of the angle. That's kind of hard to do because you have to go at a right angle. So that length, let's say 5 inches. And when we go to this side, we would have to again make it a right angle. If that really is an angle bisector, that point will be the same distance to each side of the angle. That's exactly what the theorem says. Again, pause so that you can write down the theorem. And let's draw on there like what I was just showing on the other screen. Perpendicular, each direction, those will be the same length. As long as this was an angle bisector. Second diagram, angle bisector, a point on the angle bisector, same distance this way and this way. We've constructed angle bisectors before. I think at the end of this lesson I'm reviewing that construction. Okay, so we have a couple problems. Find the value of x. Notice that on this diagram I do have the angles marked as equal or congruent, so this is an angle bisector. So the theorem says this point is going to be equidistant to each side, equal distances. So those two have to be the same. Subtract 7. Divide by 2. Lots of 4s today. X is 4. Now just to make sure it calculated right, 2 times 4 is 8 plus 7. That does come out to be 15. Next example, again, find the value of x. My markings are kind of curved, but I've got this angle congruent to this one. So point P is on that angle bisector. The distances perpendicular to the sides are the same. So to find x, 5x has to equal 3x plus 10. Subtract 3x, divide by 2. This time x is 5. And to double check, 5 times 5 is 25. 3 times 5 plus 10, 15 plus 10, that's also 25. So I do have the right answer, both lengths were 25. Okay, now I want to review there's 3 constructions here. So grab your compass and straight edge, and on your paper, let's do a perpendicular bisector. Give yourself a segment. Then from point A, make an arc. From B, do the same arc. Now we'll connect those 2 points. And you will have created a perpendicular bisector. You might notice that that's the same construction we did for midpoint or for segment bisector. Yes, you get all of those things from this one construction. Next construction is an angle bisector. So you need an angle. And you're going to bisect it again. This should be review. From the vertex of the angle, make an arc that crosses both sides of the angle. From those 2 intersection points, come out and make the same arc from each. Now when you connect the vertex through that X, that should be bisecting your angle. After you get done with the construction, grab your protractor and measure to see how accurate you were. Okay, then the perpendicular from a point to a line, this would be what we'd have to do if we wanted to get that perpendicular accurate on distance from a point to a line. So give yourself a line and a point somewhere. I went above it. Doesn't matter exactly where above it you put that. Now this perpendicular, again, I think is review, but put the point of the compass on P, swing an arc that crosses that line twice. If you got your point too far to one end, you're going to have to either move it or extend your line. Then from those 2 intersection points, make the same arc from each one of them. Connect point P through that X, and that will create a perpendicular. My sketching does not look too good. Let me sketch it again. I don't like the looks of that. But if you got it, go ahead. Okay, from point P, swing an arc. Those 2, make the X. That looks a little bit better. I need to get it moved over just a little bit. Yeah. Okay, that looks better than the first one. Creates a perpendicular through that point. Now that's not a perpendicular bisector because it doesn't cut the line in half, but you really can't cut a line in half. Lines go on forever. Okay, that's the end of the material. You will have an assignment that you need to work on next.